Yeah, I think that seems totally okay. All right. We're going to pick up where we left off last time. I think that was on slide 9. I can't remember. Do we finish slide 9 or start at slide 9? Does anybody? You think we did this one? I thought we did too. All right. I think I remember talking about Venn diagrams, right? Yeah. So I think that we did this, is just illustrating intersection and unions visually. This felt like something I talked about, but ooh boy. All right. Was that Allie in the hallway? No. Oh man. All right. So continuing on, representing a sample space. So let's look at a couple of examples here. So flip a coin twice, or if there are two separate coins, each one time, and record the results. Represent the sample space in a list form. So for flipping two coins, or one coin like once right after another, what are the possible outcomes to represent my sample space?
Heads, tails, heads.
And then head, tails, right? So that would be the 4 possible outcomes. Everybody's cool? But if a sample space is a set, we should write them with set notation. So we put the curly brackets around them. And typically use U for universal, because that's all the possible outcomes in this particular like random experiment. So what would make this into a probability model? What else do we need to have? We don't need a Venn diagram. What we need is the probability of each one of these outcomes. So if the coin is a fair coin, what is the probability of each one of these 4 outcomes? 1 in 4, like 1/4 or 0.25 or 25%. Any of the following are all equivalent. Everybody's okay there? We could also represent this in a tabular form. So for flip 1, we could get H, and then flip 2, we could get heads, and it's the same information, just represented in a table, right? Or you could represent it as a tree diagram. So our first toss, you could end up with heads or tails, and then at the second toss, if you got heads, you could get heads again. You're going to get tails. Or if you'd gotten tails on the first toss, on your second toss, you could get heads or tails again. So if I look like tails, tails, tail, head, head, tail, and then head, head. Very common way of representing like a probabilistic situations with a tree diagram. Okay. Typically, if you're representing this as a probability model, you'd put like the probability on each branch. So like in my first toss, the probability is like 0.5 of getting heads and 0.5 of getting tails. And on the second toss, it's like 0.5 of getting heads and 0.5 of getting tails. And to calculate the probability of any of these events, so like 0.5 times 0.5 would get you head, tail. 100% guaranteed you'll be using tree diagrams to calculate probabilities in this chapter on the test, quiz, etc. likely see it on the IB exam, very common presentation. And then the other is, the last one I think is with a Venn diagram. So again, our universal set, and then just the 4 outcomes. This is like the most boring Venn diagram you've ever seen because there's only one, only one set. There's no overlapping parts. It's literally just like the circle with the 4 outcomes drawn in it. A lot of times there'll be 2 circles. There could be 3, could be 4, depending on the situation. But this is like a really simple example. We could also give it as a probability table. So my first toss, I could get heads or tails. Second toss, I could get heads or tails. So my outcomes would be like head, head, tail, head, head, tail, tail, tail. Notice that I listed in the ordered pairs here, the first toss outcome is the number that's written first. So here at the first toss was heads. I have heads as the x coordinate. For this first toss was tails. The tails is written as the x coordinate. Everybody's okay there? Okay. So all of those different presentations are all representing the same information, right? You'll have to be able to, in the homework and quiz and test and stuff, be able to work with any of those kind of presentations. So it's really the same problem, it's just like how they're going to give you the information. Everybody's okay? So let's do another example. When rolling a standard 6-sided die, what is the set of event A that we observe an odd number? So what outcomes go into event A? 1, 3, and 5. So we'll write that with set notation. We'll call this A for event A. We use capital letter to represent a set. We just write in set notation. Feel good? How about event B is we observe a number less than 5. What would event B, what outcomes would be contained in event B? 1 through 4. Okay? Everybody feel good there? What if event C is the intersection of A and B? What would be contained in event C? 1 and 3. The numbers in common to both sets. Everybody feel good there? Okay. What about the complement of A? Remember, complement is not. It really means the same thing as not. So we want the outcomes that are not in A. 2, 4, 6. Everybody feel good there? Okay. How about A union B complement? So it's going to be everything in A, and then everything not in B. So what's 5? So 5 and 6 is the stuff that's not in B, right? But this is a union, not an intersection, so it's all of that stuff. So it's 1, 3, 5, and 6. Remember, even though 5 occurs twice, we don't list 5 twice. Very important that you don't repeat any elements when you write your set. Sets are non-repeating. So far, so good? Okay. Using words, interpret event E. So it's the set of numbers on a standard 6-sided die that are an odd number or a number that is not less than 5. So the or was for the union, and the not is for the complement symbol. And I just read I basically read what event A is. And then event B, I just inserted the not for the complement, and I inserted an or between them when I got to the union. Is everybody okay there? Oh. Yeah, fancy. All right, so some basic identities that are helpful with set theories. Given that A is or U is the universal and this guy, the null symbol, is the empty set. If I have the intersection of A and B, that's the same thing as the intersection of B and A. So the intersection is commutative, just like addition. The union of A and B is also equal to the union of B and A, also commutative. The complement of a complement is just A, like the negative of a negative. A intersect the union is just going to be A. So intersecting the union is kind of like times 1, or adding 0. A union, the universal, is going to just be the universal. It's like multiplying by 0. Like anything union, the universal is just the universal. A intersect its complement is going to be the empty set. A union its complement is going to be the universal. And then we have two other special properties known as De Morgan's laws. So that is that if I have the complement of a union, that's the intersection of the complements. So that complement symbol distributes, and it flips. And if you had the complement or the complement of an intersection, that's going to be the union of the complements. Does everybody feel okay there? So these are just some basic identities. Let's take a look at some more examples. So we have two tetrahedral dice with sides numbered 1 through 4. So that's just two 4-sided die. One is blue and one is yellow. And we're rolling them. So why are the colors going to be important? It's so you can tell the difference between like a 1 and a 1, right? If one dice is blue and the other is yellow, I can tell 1 is different than a blue 1, and yellow 1 is different than a yellow 1 and a blue 1, right? I should say 1-4, right? A yellow 1 and a blue 4 is different than a blue 1 and a yellow 4. That's a better example. All right, our first event is T is equal to at least one dice lands on 3. Okay, so let's start by drawing out our sample space. So let's do, it said we used the table this time, is what I did. So I could have a blue 1, 2, 3, or 4. I could have a yellow 1, 2, 3, or 4. And it looks like I've used the yellow dice as the x coordinate and the blue dice as the y coordinate. Right? Because when I look at the 2 column or the 2 row, all the 2's are first. Everybody's okay with that? So this is my sample space. How many of these outcomes have at least one die with a 3 on it? So I have this one, this one, this one, this one, and then this one, and this one. Everybody agree? Remember that no repeats, so 3, 3 I only list once. But that's my event for T, is the set containing these 7 outcomes. Everybody feel okay there? Okay. We'll call event B, the blue dice lands on 3. So that's going to be these 4, right? Those are the only ones where the blue dice lands on a 3. So far, so good. And notice that the order in which I write these outcomes does not matter. Sets are not ordered. Now I wrote them in like just going down the table order, but it would be still correct if you had 1, 3 last and 4, 3 first. Like it doesn't, the order in which you write them, the outcomes in your set doesn't matter. Oops. The next one is the sum of the die is 6. So I see 4 plus 2, 3 plus 3, and 2 plus 4. Those are the only ones that add up to give me 6. So that's set S. And that seems to be the end of that PowerPoint. Let's go through and do some of our in-class examples here for the chapter, and then we'll probably call her a day. Yes. Isn't it awesome? Yeah, I know. I'm super excited that it happens to my projector like all the time. I keep forgetting to talk to IT about it. One of these days I'm going to have to remember. But here's the weird thing. What's going to happen is I'm going to turn this off and like come back like an hour later and won't do it again. So it's like one of those things, like I feel like I'm going to call him down here to ask him about it, and then it won't do it for me. I'll look like a crazy person. Which is always, feels like just my luck. All right, so let's look at a couple of examples here. So it says, suppose that exactly 5% of a specific cell phone under warranty will be returned, and the cost to replace the phone is $150. If the manufacturer knew which phones would go bad, they just charge a $150 warranty for those phones, and then charge everyone else $0. However, the manufacturer can't know which phones will need to be replaced. If the manufacturer wishes to be as fair as possible, how much should they charge for a warranty for every customer? What's that? To everybody? Well, they're going to be overcharging everyone, right? We said we want to do it as fairly as possible. Sure, they could do that.
$7.50.
Yeah, how did you come up with $7.50?
Because it's exactly 120 phones, so just about 150.
So you did 5% of 150, right? So if 5% of the time the phone goes bad, we need to replace it, then everyone's warranty should be 5% of the replacement cost. If everybody pays $750, then the amount of warranty money that's come in should cover exactly, the 5% of phones that need to be replaced at $150 a pop. Does that feel okay? It's much the same way, like, if you've ever watched people playing like poker on television, they used to televise this on ESPN all the time in the summer when they didn't have anything else to show. But you'd hear the announcers talk about the players being like pot committed. By that, they mean that the probability of them winning the hand and the money that they win is greater than the bet that they have to call. So it's like it makes no sense to fold here because the probability of you winning times the money in the pot is greater than what you're paying to stay in the hand, which means that like if you're a smart gambler, you should get positive return playing that in the long run. It's much in the same way. I don't know if you're interested in internet gambling at all. Seems like everybody is. All right. Huh?
I went to play some poker last night.
You went to play poker last night. It's like, where were you yesterday? All right. The next one, we say that a die is rolled 12 times, and we've recorded below the results of each roll. Which of the following outcomes is more probable? I got 1, 2, 3, 4, 5, 6, 6, 5, 4, 3, 2, 1. And the other sequence I got was 1, 5, 4, 5, 2, 4, 3, 3, 6, 1, 2, 6. Which set of outcomes of rolling one die 12 times seems more or less likely? Great. It was a trick question. They're both equally likely because these are independent events, right? The rolling of the die on the second roll doesn't affect the outcome for the die in the third roll. If you look, it's the same number of ones rolled, both have 2 1s. The same number of 2s rolled, they both have 2 2s. The same number of 3s are rolled. These are identical. The order in which they're rolled makes no difference in the likelihood. They have the same outcomes. The sequence of outcomes does not matter. Everybody feel okay there? Okay. In casinos, there's often a large display next to every roulette table showing the outcomes of the previous spins of the wheel. The results of previous spins have no effect on the results of future spins. So why do casinos use these displays?
To get people to think that it's like pound for jackpot.
Yeah, to trick gamblers into believing that a number or a color or something is due. What this is violating is that law of short-term regularity, right? That the probabilities in the short term should match the probability in the long term. Not the case. Oops. Guess this was left over that I forgot to erase. Well, let's just write it down and we'll just talk about it. Give the probability model for flipping a fair coin 3 times. You may list your sample space in whatever manner you choose. So technically, we should also have we should have the curly brackets around this. So I just listed it systematically. All the ways you could write 3 heads. Well, there's just one way to do that. All the ways you could list 2 heads. Well, there's just 2 ways to do that. Oh, 3 ways. I guess what did I do? Oh, I did it where heads is first, right? And then heads is second. And there's 2 ways to list with heads. And then if heads is first and tails is second, well, there's 2 ways to do that. Actually, this looks like just somebody listed them. Some kid listed them for me, and I wrote it down. This doesn't look systematic at all. Anyway, from a counting standpoint, if I have 2 possible outcomes and I do it 3 times, how many total should I have? 2 to the third. So you have 8 total, which is often helpful for did I find all the possible outcomes here? Right? If something has 6 outcomes and you did it 5 times, how many outcomes should you have? 6 to the 5th. Yikes, that's going to be a big number. But that's a general counting principle that's often helpful, and just double checking to make sure that we counted them all. All right. Well, you didn't see nothing. So it says the universal set is all the integers 1 through 10 inclusive. A is the even numbers between 1 and 10 inclusive. And B is the set 2, 3, 5, and 7. Draw a Venn diagram that relates the sets above. So you want to start by kind of drawing your rectangle. And we'll put the U in the corner for the universal. And we'll draw our 2 overlapping circles. Even if they don't end up having any elements in common, we'll draw it this way anyways. And if there's nothing to write in there, there's nothing to write in there. And now you'd want to start with the intersection between A and B. Is there anything that falls in the intersection of A and B? The number 2. Okay? All right. What are the things that are the other things in A that are not in B? So that's going to be this space here. What else is in A that we haven't listed yet? 4, 6, 8, and 10, right? Everybody's okay there? How about the things that are in B but not A? What else goes in here? 3, 5, and 7. And then anything that we haven't listed so far, 9. So that's going to live out here, outside of either circle. You guys feel good on how we built that out? Again, you want to work from the intersection out. You know, fill in the intersection, fill in set A, the rest of set B, and then anything left over goes outside there. All right. It says use the Venn diagram below to shade the following sets. So set A, or the first problem here, asks us to shade A complement. What does A complement mean? Not in A. So I'm just going to shade all of the Venn diagram that's not A. Everybody's okay with that? Okay. Actually, I'll just use a bunch of colors and this will get wacky, but it'll be okay. You? Come on now. Nobody wants to pick up and move this thing. All right. B is A union B complement. So what is the stuff that's not in A union B? It's not everything but the intersection. It's everything that's not a circle. Right? A union B is both circles. So the complement of that is not the circles. Come on. All right. A intersect, not B. So what's part of not B that's also part of A? It's like that stuff, right? That's not in B, and also part of A.
Yeah.
Oops, we need a new color. How about not in A or in B?
It's just all outside.
It's more than just all the I don't like that. Looks too much like red. Do that color. Ugh.
Oh, yeah, all outside.
not just half of B, all of B. Right? The union is or, so it's all the stuff outside of A.
Isn't A also include school stuff?
Right. So part of A is included because that part of A that I did include is part of B. Right? The union is or,
Oh, yeah.
so it's all of B and then the stuff not in A.
Gotcha.
And then our last one, we'll use this. So A intersect, or the complement of A intersect B. So where's A intersect B? That's the overlap, right? So not the overlap. It'd be like that. Does that feel okay? It's a crazy looking picture now with all the colors. Uh-oh. All right. All right. So let's see. Example 7 says there are 40 students at an IB school that are studying either chemistry or biology or both. 25 of the students are studying chemistry, 19 are studying biology, 4 are studying both. Represent that information as a Venn diagram. I don't know why this is obsessed with like thinking I want to move stuff. All right. So do that. So I'll call this one C and this one B for chemistry and biology. We've said we want to start with labeling the inside out. So what's going to go in the intersection? What's going to go in the intersection? How many students? Okay. How many are going to go in this spot? Okay, so if I put 25 there, how many students total are taking chemistry then? 29. How many does the problem say are taking chemistry? 25, right?
Yes, you have 21.
Yeah, so it should be 21. Good, because we've already placed 4 students in chemistry, right? In the intersection.
15 taking bio.
Good. If I add those up, I get how much total?
40.
40, which is what I'm supposed to get total, right? Okay. We've represented the information as a Venn diagram. Also wants it as a two-way table. How many are studying just chemistry and how many are studying just biology? Well, we figured that out already, right? So our two-way table is going to look like... So chemistry, not chemistry, biology, not biology, and then we'll have like a total. Okay, we know that 4 take chemistry and biology. We know 25 total take chemistry. We know there's 40 total in the school, we know 19 students take take biology. Everybody's okay with what I filled in so far? That's just from the givens. So this piece here, 4 plus 15 should give me 19. 4 plus 21 should give me 25. 19 plus 21 should give me 40. 21 plus 0 gives me 21. 15 plus 0 gives me 15. If I check now, everything adds total-wise. You guys feel okay with how I filled that in? Very common as part of a problem to have to do one or both of these, like complete the rest of the Venn diagram from the story or complete the rest of the two-way table from the story. It's essentially the same problem, it's just like a different presentation, right? To fill in the two-way table, we did exactly the same things that we did to fill in the Venn diagram, right? All right. So example 8 says there's 50 people in a band. The conductor wants to know who can play the saxophone, who can play the trumpet, and who can play the drums. He finds out that 2 people play all 3, 5 people play just the saxophone and the trumpet, 1 person can play just the saxophone and the drums, 3 people can play just the drums and trumpet, 22 people play trumpet, 15 play drums, 18 play saxophone. Represent this as a Venn diagram. Okay, we'll start there. How many circles is this Venn diagram going to have, though? It's going to have 3, right? See, so we'll name this guy saxophone, trumpet, drums. Everybody feel okay with how I drew my picture there? Okay. So let's start from the inside out. So the triple intersection is here, correct? What should go in the triple intersection? 2, because 2 people can play all 3. Next, let's look at the intersection between drum and trumpet. So that's that spot. Or I'm sorry, yeah, that's drum and trumpet. I said just look at the intersection between drum and trumpet.
Okay.
So we want to fill in this spot here, and that should be 5 because that spot is just drum and trumpet. Does that feel okay? If we look at the intersection between saxophone and drums, that's this spot. If we want to fill this in, that's just drum and saxophone. So that should be a 1. And then we'll look at the intersection between saxophone and trumpet.
That's the 5. Drum and trumpet should be 3.
Sorry. I put it in the wrong spot, huh? Thank you. So this was supposed to be the 5, and that was supposed to be the next one, the 3. Excuse me. Okay. All right. Next it says 22 people can play the trumpet. So this circle needs to contain 22. How many have we placed in that circle so far? 10. So what needs to go in this spot here? 12. And then 15 can play the drums. So that's that circle. How many have we placed already? How many left do we need to place? 15. So 9 more. And then this circle is saxophone. 18 for saxophone. How many have we placed? How many left? 10. Okay. And then we should check now who can't play any of these three, right? Because we know there's 50 total people. We've placed 10, 11, 20, 3, 5, 30, 42. Where the other 8 people have to go.
Outside.
Yeah. Everybody feel good? Don't forget to check for the nobodies, right? The people that don't go in any circle. Easy to forget to do that. How many people play none of these instruments? Well, we just found it out. What is it? 8. How many people are in the union of S and T? So the union of S and T is that, right?
Yeah.
So we'd have 1, 3, 16, 21, 33. Oops. And then what's the probability of selecting a student that plays saxophone or trumpet? So that should be 33 out of 50, which is just the number in S union T over the number in the universal. Everybody feel so far so good? Again, like most of this stuff isn't difficult, but it's different. We probably haven't done anything with a Venn diagram since we're in like middle school or something. Most of this is just like getting comfortable with the vocabularies and the notations and like, what do we do with this stuff again? All right. One more. Says there are 105 people in the same grade as each other. The teacher finds out some students are in the same math class, science class, and English class. She finds out that, 4 students are in all classes together, 12 are in math and science together, 5 are in science and English together, 9 are in math and English together, 40 in math, 26 in science, 50 in English. Represent this as a Venn diagram. So let's say math, science, English, universal. Okay. Where do we start? The triple intersection. How many go there? 4. Okay. The next says 12 total are in math and science together. So the intersection of math and science is here. We've placed 4 already. So what needs to go in the other spot? 8. Science and English is the next one. That's this intersection. We've placed 4 already. Where do we have to have 5 total. So the other spot needs 1 more person. And then English and math and English is this section. There's 9 total there. We've already placed 4, so the remaining spot needs to contain 5. 40 are in math. We've already placed 17, so 23 more. 26 are in science. We've placed 13, so we need to place 13 more. 50 are in English. We've placed 10, so we need to place 40 more. There were 105 students altogether. We've placed 41, 45, 50, 73, 81, 94. So that makes 11 left over. So we did this. The number of students not in math and also in English. So we want the stuff that's in English but not in math, which would be that spot, right? Does everybody feel okay there? Now it's starting to get complicated, so we want in math or science. So that's that spot, intersecting the stuff that's not in English. So we're chopping off the stuff that's in English. So it's the 23, the 8, and the 13. So that's 31, 44. Okay. So not science and not math. So that's going to be here and the outsides. Everybody's okay that? And then union with the English. So I'm adding back in all of English. So that's going to be 61. Is everybody okay? So again, just like kind of drawing or doing some shading, I think is, oops, those are supposed to be probabilities, right? So I just divide these by 105 then. But that's the idea. You guys feel okay with what we've done today? Okay. I'm going to stop here. It feels like everybody's kind of cook-a-rooskied, judging by the current level of engagement. So we'll stop here. You guys can take your remaining 40 minutes or so of class and start in on the 8-1 problems from the textbook. My suggestion to you guys, these are unfamiliar enough and not really calculator type problems that you probably really want to do these instead of just copying answers out of the back of the book. Not saying that anybody's been doing that, but I'm not so naive enough to think that the answers aren't back there, and you might do a little bit and then just do a lot of copying after you're like, yeah, I've done this problem 3 times now. The presentation here can be changed up quite a bit depending on how they're describing what's going on and what they're asking you to complete or fill in. I'd recommend really for this chapter actually trying to do these problems and checking in the back of the book. If you haven't already been doing that, which I know we all have because we're just dedicated and excellent math students. Today was supposed to be the due date for the intro redo if you were redoing that. If you haven't done that already, I'll accept through the end of the day. If you want to take your 40 minutes and try to like plow through that, that would be okay. My hope is that Tuesday or Thursday next week we'll start doing showing you guys how to do the data analysis for your IA. I've asked now all of my classes to fill out surveys that are seniors and incentivize them with some test extra credit to do so. Those of you that have a survey, can anybody check their number of responses to give me an idea of how successful we've been and how much more?
68.
68 is great. 47, great. Okay, those are real good. That's good numbers. So should be plugging away. I'll ask. Yeah, good. I'll ask Miss Garcia to ask her HL kids if they can fill out some, and I can ask Miss Morgan. I don't know that Miss Morgan has the personal. I don't know what she has right now, but I'll talk to Miss Garcia because I know she has a group of all seniors for HLs, and probably AP stats is mostly seniors as well.
My number is interesting.
You may have some that just get thrown out.
Yep, I was gonna say, I've got someone who has 9 rows.
What is that a lot?
A lot. That's why I made sure to make my full article.
Yeah. Mm.
For the IA, do you want us to like